brief AV hiccup. We are back with Tom, who is talking about why UUIDs are secretly incredibly fascinating. Please make Tom welcome.
Hello, I'm weirdly nervous this morning. Most of the talks that I give have a kind of point. This one was purely sort of special interest information dumping. So I ended up just talking about this randomly to random people forever, and so now you guys are forced to sit here and listen to it. In terms of real-world information, if you've already read RFC 9562, then you probably already know everything that I'm going to say in this talk, and you're just kind of here for opinions and vibes, I guess. Because I yammer on about this way too much, I've got the last slide of my talk first, just in case I go over time. So, most of this is just weird interest stuff, but like, if there's useful things that I want you to take out of it, if there's useful things that I want you to take from this talk, they are that it's really worth knowing what the differences between these UUIDs are, because they can actually be quite useful for certain use cases. And UUID v7, which is a new standard that was finalized in April of this year, but has been being worked on for the last couple of years, might be really useful for certain use cases of yours, and we'll go into more details on that later. If you need to invent your own kind of universal ID system, there's now a spec for you to conform to while you do that, which could be very useful for you, so make sure you know about that. But I'm talking about a thing that may or may not be useful to you depending on your use case. So probably the most important lesson that I realized is probably applicable to almost everyone in this room if you work in what we do. Whether or not UUIDs are a good primary key for you or not, or whether or not they're useful for your use case, I've now worked in a couple places where we've had real problems with the default primary key value of databases, particularly Postgres. So maybe you don't, the one lesson that I think is probably applicable to everyone is maybe you don't need 128-bit universally unique identifiers, but I think that nowadays you will regret using a 32-bit identifier at some point, and by the time you regret it, it's a really painful job to fix. So cool, you can all go now. Okay. I don't know why I wasn't able to squeeze this all into a lightning talk. So why am I talking about this? Because I thought this was really interesting. In Django land, first of all, how many people here work in Django, do web development, do database design, have to choose your primary key? Yeah, okay, so you guys are vaguely in the right place, right? You get really used to Django's defaults of integer primary keys. If you don't decide on one, it'll make one for you, and by and large, it works perfectly fine forever until your table gets too big. I've now worked at 3 different companies where each one has had huge projects that have each one taken like over a year of developer time because of something going fun with your primary key choice. I worked for a company several years ago who were merging multiple production environments into one production environment, which was multi-tenanted, and naturally they had to remap a whole bunch of primary keys through a huge amounts of data sets, and it was gigantic, and talking about that would be a whole talk on its own. I've worked for a company that chose to use UUID 4s and text columns for every primary key in every table of their database, which had some real, I see some of you shaking your heads, and you're right, but also it had some real advantages that I will also go into. And then most recently, at Kraken Technologies, we've had an amazing project recently where we've had to, with some urgency, quite quickly change a bunch of primary keys from 32-bit integers to 64-bit integers because we were running out of space. And by the time you're running out of space, your tables are already really big. And if your tables are really big, it's probably because you've been reasonably successful, so you don't want downtime. And so trying to do this sort of thing without downtime would also be a whole big talk of its own. Tim Bell will be here later in the conference, and I'm sure he'll love to revisit many months of his life. So be sure to ask him about it. For a long time, all I really knew about UUIDs was that they looked like this. You know, you've got those hyphens in slightly different places. You've got a whole string of hexadecimal numbers, and there's a bunch of different versions of them. And in practice, you only ever really see UUID v4, which is the version which is completely random. Who here, like, I don't go into much about where they came from. I just go into sort of the weird stuff in this talk. But all of you have seen this sort of thing before, yeah. I knew about UUID v1s. I knew that they were constructed from several ingredients. And I knew that people like just don't use them for anything. And then if you go into the Python standard library, you'll see UUID versions 2, 3, and 5. Didn't know what they were. And nobody uses them. And so that was what really got me interested. We've had this standard. UUIDs have been around and not a standard since like 1995, and they've been a standard since 2002 or 2004, and nobody uses them, and everybody invents their own. Twitter invented lexical UUID and Snowflake, and Google invented push ID for Firebase, and doc ID, which is something they use in Google Drive, and MongoDB invented their own ones, and Instagram, which is a big Python Django project, invented their own one called sharding ID. Everyone has to invent their own because for some reason the standard that we had was never fit for purpose. So I am going to give you a crash course in what all of these things were, why they're interesting, why they weren't fit for purpose, and how that's being fixed nowadays. So this is the executive summary of all the versions that are currently in Python. The V1 was built out of the timestamp, the MAC address, and the sequence, and so each of those chunks of the UUID become those things. The V4 is the completely random one that doesn't use any other kind of logic. It's just 121 bits of completely random information, and then the little version specifier, which is like whatever the remaining bits were, 7 bits, right? V3 and V5 are the ones that you probably heard the least about, and they have a very interesting niche use case because you can turn any other identifier you've got into a UUID. I'll show you an example of that. And V2 I'm not going to talk about because it's almost the same as V1, but it was specific for a certain application back in the 90s for a certain operating system. So none of it really exists anymore, so it's something that you can actually just kind of ignore. So we'll talk about V1. They decided that a universal ID, something that, well, hang on. The point of a universal ID is that you can have a lot of things generating these IDs and they'll never collide, okay? One easy way of doing that is making sure that you incorporate a few ingredients that the other machines generating UUIDs won't have. So the time that it was generated, a node ID, like a machine ID, and so each machine generating UUIDs has its own node ID, and then a few other bits and pieces, like sometimes a bit of random data or a clock sequence. When they were designing UUID ones, they made a couple interesting decisions that kind of came back to haunt them. The timestamp, is this readable for people? Cool, okay. The timestamp is a 60-bit value. For UUID1, this is represented by the coordinated usable time, blah, 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 blah. 100 nanosecond intervals since the Gregorian reform to the Christian calendar in 1582. Okay, sure, why not? And then the node address was the MAC address of your computer. So just find any network card on your computer, grab its MAC address, and throw it into the ID. So this example, this UUID right here is the one that's like in the spec. And if you can decode it and get that information back out, the spec suggests that you don't do this, that you don't rely on any information in the UUID, but it's interesting that you can decode it. And so you can find out that the time that this UUID was generated was the 3rd of February, 1997. The clock sequence, which is actually just kind of a random number, is 10085. And the node ID is that network address. And of course, because it's a network address, you can also tell that that's from Intel. It's from an Intel Corporation machine, and that block of MAC addresses was allocated on the 1st of January 1980, like around the first allocations of Ethernet addresses. The reason you can know that, by the way, is because maybe up until recently, or maybe it is still the case, that all MAC addresses, the first half of it, are allocated to a network card manufacturer, and they get to decide on the sequence number from there. So the other important thing to note is the time in UUID1s is backwards. So it's not like year first, then month, then day, or it's not most significant bit first, it's least significant bit first. So they don't enter in order. So UUID 1s could, their sort of overall numerical value could be all over the show as the least significant digits increment. That will be important. So that's UUID 1. I've skipped over UUID 4 because it's just pure random data. I told you that UUID 5 is quite an interesting one. Sometimes you have a use case for this, and I did have a use case for this, and it was great. You take any other identifier you've got, and you turn it into a UUID. And so you do that by, the way the algorithm works is it takes a namespace, which is just another UUID, and it takes the canonical representation of your value, of your name, and it does something like an HMAC. You know, it does like, it concatenates the two, and then it does a SHA-1 hash or an MD5 hash, and it takes those bits and turns that into a UUID. The difference between V3 and V5 is that V5 used MD5 and V5 used SHA-1, and so they don't recommend you use V3 anymore at all, but it's still around in the standard. And so, and in the standard, there's a couple predefined namespaces. So if you, for some reason, wanted to turn a DNS name into a UUID, there's a DNS namespace, and there's a URL namespace, and there's a X509 namespace, and a few other things. And so this can actually be genuinely useful. And I did this trick a couple years ago because I had a primary key that I needed to turn into a UUID for a certain table. And the integer ID corresponded to a sequence of financial transactions. And you invent any UUID, and it becomes your namespace for whatever the identifier is that you have. And from then on, you can basically just map anything onto any name in there to a UUID without it colliding. So they're deterministic this way. So unlike the other ones where you expect to get a different unique UUID every time, these are designed to get you back to the same one every time. So for transaction 1, as you can see, I've got the same value. You can see my mouse, yep. Okay, transaction 1, you can see the same value came out when you feed it the same input. Transaction 2 is a completely different ID. So you can't, so basically a one-way hash, right? Basically like a password hash. Hang on, let me just. And UUID 4, pure random data. And so nobody uses these, except UUID 4 is still fairly commonly used when you just want purely random stuff. A lot of the time people wonder if collisions were why you wouldn't want to use these, if they were too likely to collide. If you go to the Wikipedia page, you'll see various absurd examples of, what is it, like with UUID 4, which is completely random, if you generated 1 billion of them a minute, or no, 1 billion a second for 90 years, you'd have a coin flip chance of maybe having generated 2 of the same one. So the numbers that we're talking about for random collisions in a way that would affect your app are negligible. Like humans really don't have a great way of understanding in their head just how gigantic a 128-bit number is. But in the history of people using UUIDs, there have been collisions, but they've always been sort of implementation bugs. So a reasonably prominent example was, I think, it might not have been VMware, but it was like a VM company product that was incorrectly seeding the random number entropy pool on booting VMs, and so the VMs had a higher chance of generating the same UUIDs. So there's been that sort of thing in the past, but that's not why these became unused. It was because, by and large, everybody needed one feature of identifiers that UUIDs didn't provide, which was they needed numbers to go up. Especially, so a perfect example of this is a relational database like Postgres. I use Postgres for all my examples because I just use Postgres for everything. Most relational databases use B-trees for their indexes, and B-trees have been heavily optimized for insertions kind of happening at the end of the stack. And so in real world terms, you want locality of data that was sort of generated around the same time. And so you would like your IDs for similar data to be close to each other on disk or logically. UUID, the UUID standard, all of those numbers come out pretty much random, including the UUID v1, which had time, but like I told you, the time was backwards. So the lowest significant bits are wrapping around all the time. Inserts will happen all through the table. Inserts will happen all through the index, and that's fairly inefficient. Some other complaints, UUID v1, the Gregorian epoch thing just was annoying to implement. If you did want to sort them by order, you kind of had to parse the UUID, which is not a great idea. And using the MAC address was considered a bad idea. People either wanted kind of arbitrary node IDs that they assigned, or they really didn't want the potential security or identity problems of using your literal network address in your primary keys. And so, yeah, if we went back to that list, all those Twitter ones, and I think the MongoDB ones, all of them are like 64-bit integers that basically have some variation of like the time and then random data, but the time is in correct order so that basically IDs will go up over time. Yeah, Snowflake has a little bit of extra data in the middle. It's used by Mastodon as well for those who use that. It's like the time, a type identifier, and then random data. But the thing that ended up being really popular was time, so that number basically goes up as you generate them, and random data. So that brings us finally to the new versions. The new versions will probably be in Python by 3.14. There's pull requests for them, and I see discussions on like the Python discussion lists. But there's plenty of libraries that use them anyway. Oh yeah, I was going to demonstrate some of these. I even have like a terminal right here. Look, there you go, UUID ones. Actually, yeah, let's do this now. So I just generated 20 UUID ones, and what you can see is that they're actually not that unique, right? Like you can see that the time sequence is going up on the left, and as soon as that, actually, yeah, perfect timing. Let's just hang on. I always go over time, and now I'm suggesting we wait. I always go over time when I'm talking about this. And now if I just sit here for a little bit longer, it's going to take too long. But you can see what's going to happen. The D is going to wrap around to E, and then it's going to wrap around to F, and then it's going to wrap back around to 0. And so that means that the insertions of these IDs, as they were being generated all over the place, they're not going to be at the end of the index. Now, if we used UUID 4, they're completely random. Right, so they're also always going to be inserted in random places in your index. Except for, as you can see, the little 4 down here, which is the version specifier. And the other non-random bit is this column here, you'll notice, is never lower than 8 in hexadecimal value because the first 2 bits of that number are also part of the version specifier. So they're never quite as random as you totally thought. Anyway, let's go on to the new ones. UUID v6 is exactly the same as UUID v1, except put the time in the right order. So it's still the Gregorian 100 nanosecond thingamabob. But you put the time in the correct order, and the spec says don't use the network ID anymore. Just pick a random number and stick to it. So can I generate some of these for you? Yeah, if we go, what do they look like? They are going up over time. Oh, and this implementation, as you can see, it's not sticking to a static node ID. This last chunk here is the node ID. And it's not, so they're just generating a random one each time. But the point of the UUID v6, they don't recommend you use it, they just invented it because it's literally just UUID v1 with the bits rearranged so that you can implement it really easily. If all you've got is UUID v1s, you can just take that, move this bit to here, and then you're done. UUID v7 is the one that they recommend you use for everything nowadays. And it's really dumb simple. It is just the Unix timestamp, the number of milliseconds since the January 1st, 1970, which pretty much every modern computer just uses. You all are familiar with it. Unix timestamp in milliseconds for the first 48 bits, and then a big chunk of random data. Like, it's still a big chunk because you got 48 bits, then you got like, what, 67 bits of random data? So that's enough to make it really unguessable. And then there's a couple optional rules in there for sub-millisecond precision. So like this little chunk right here, instead of just being a part of the random data, can be, if your system clock goes down to nanosecond precision, you can kind of use that for some more time precision. I'll generate a couple of those, and you'll see more numbers on screen. Won't that be exciting? And they are very random, except for that front part, and they go up over time. And they're guaranteed to go up over time. That's the other rule of UUID v7 is if it's written into the rules that implementations need to account for like clock jitter and stuff and need to either increment a counter, but you can place design guarantees that it will go up over time. And finally, they created a UUID v8. And UUID v8 is, screw it, build your own. You can decide what any of these bits are. You can decide what chunks they are. They just have to have the version bit in the right spot and the variant bit in the right spot. And this sounds like it might be a bit of a cop-out, but it's actually incredibly useful because 128 bits is probably, you can construct a really useful identifier out of that. You might need to put some kind of implementation-specific information in it. But having a UUID spec for it means that you can use things like Postgres's native binary UUID column and indexes for it. And so this is actually, might actually be a really powerful, useful new tool for people who do have to invent their own identifiers for something because you don't have to stash them in big strings in your Postgres database. So it's kind of the general purpose, do whatever you want, and they still recommend that you don't depend on what information is in there. Like, you shouldn't really be decoding these things anyway as a best practice. But by having that, you can use Python's UUID type. You can, database native formats that support it. Those are the new versions. So for the last bit of my talk, I'm going to talk about like why you may or may not want to use these in your database primary key. You don't need UUIDs until your project or your data set or your system is so big or distributed that you can't afford the time or network cost of asking permission to use a given identifier as a primary key, right? Postgres by design, your primary key is always going into index with like a uniqueness constraint on it, right? So no matter what, even if you're using UUIDs in your Postgres database, you're still kind of asking permission if you can use that identifier because you're checking to see if it can go into your index, and if it can't, then there's a collision. So UUIDs aren't designed for this use case, but they're good for it anyway. There's some real advantages. Migrating your primary keys when you realize they're not fit for purpose is a really expensive project. The thing that I was just telling you before about moving from 32-bit to 64-bit integers. By the time you've got billions of rows in your database and you don't want your database to have downtime, you're in real trouble there. By the time you realize you have to do it, your database is always really, really big. This one fascinated me. This was the big lesson that I got for working for a company that had just off the bat, because it wasn't a Django project, probably, they just were like, nope, we're going to use UUIDs as our primary keys for every table. It was a company that also dropped to raw SQL all the time, quite usefully. Like, it was an SQL alchemy project, and so that meant that it's quite easy for you to go use the ORM when it's convenient, but also when you have a query of some complexity that you want to construct. The convention was that you feel quite casual about dropping down to raw SQL to write it. But when you're writing raw SQL with a modern database schema, there's a lot of risk of like doing the wrong join on the wrong identifier. You might have several models that are like closely related, closely stacked, and you might join the wrong one on the wrong one. And if every table has a row in it of ID 100, you won't notice that you've made this mistake. A real advantage of your primary keys being globally unique, at least in terms of your entire application and not just your individual tables, is that entire class of bugs is just eliminated because a developer will write a join and it won't get any rows, and they'll go, oh, because I'm joining on the wrong foreign key. And so I've got no idea how much time that saved us, because it's one of those things like the bug can't happen, so it didn't happen, so I don't know how much time we saved, but I've had that bug in the past, and so working for a company for a couple of years where that sort of thing just didn't happen, you don't really know how much it bought us, but it was not nothing. If you are using UUIDs in your database, don't store them as strings. If you store them as strings, instead of being like, 16 bytes of binary data, it's about 56 bytes, including the hyphen. A UUID with all capital letters is a different UUID than a UUID with all lowercase letters, and that's not great. And you're looking up collation rules every time you do any kind of comparison or database index or B-tree insertion or anything, which means effectively that when you're inserting a UUID into your table, it has to check if it's like a Mexican UUID or a Polish UUID or a UTF-8 UUID, because you order the letters in a different way when actually you just want to be treating them as binary data. So other piece of solid advice, if you're using Postgres and you want to use UUIDs, use the UUID column. Way faster, way more efficient. And yeah, I've now built a couple databases just for side projects with using UUID 7 as a primary key. Yeah, it works, and you don't have to think about it. It's just like, sure, okay. But of course, this is something with like a couple million rows, so it's not like my little side project that's collecting the temperature sensor in my bathroom is going to hit 2 billion rows anytime soon. And then V4 is still useful for completely unguessable stuff. V5, keep an eye on V5. Sometimes you might go, oh, actually, I have a use for this. Where are we? Yeah, and if you need to invent your own, seriously consider using UUID v8 because it lets you use Postgres's column. It lets you use all this tooling that you've already got. And then finally, yeah, the only bit of absolute solid advice that I think I have for you is, if you work for a company, you might end up with a couple billion rows sooner than you think. And so UUIDs might not be the right answer, but 32-bit integers, you're saving yourself 4 bytes a row, right? Or 8 bytes a row if it's indexed as well. For small tables, that's not very much. And for big tables, you'll wish you had changed it. So the one piece of advice I have for you is move away from the small numbers for your primary keys. And that's my entire slide deck. I am done. We have a minute for questions.
Thank you, Tom. We are unfortunately out of time for questions.
Cool.
We have a gift for you as a token of appreciation.
That is gorgeous. Thank you very much.
That is the only mugging allowed. And thank you very much.
I'll be hanging out at the Kraken desk some of the time this weekend, and otherwise just come and grab me at any moment if you want to chat. Thank you so much for your time. Thank you.